Hello, I'm going to describe figure 7.7 in Kaiser et al.'s Marine Ecology Processes, Systems and Impacts. So figure 7.7 shows the stomal diagram, and what this diagram tries to do is show how various factors in the ocean change on a range of time and space scales, and to convey how time and space variability are really intrinsically interlinked. So on the x-axis of this diagram is time, and it's in a logarithmic scale going from 10 to the 0 to 10 to the 12, which spans seconds to tens of thousands of years. On the y scale, we've got a logarithmic scale of length. This goes from 1 centimetre up to 10,000 kilometres. And in the z dimension, and you can see the contours on the grid trying to show this z dimension, we've got variability in biomass. And so what this image effectively does is convey all of the variability that we would see over multiple thousands of years and multiple thousands of kilometres together. So an interesting feature to note is that at the daily scale, around about 10 to the 4 in time, we've got this phenomenon of diel vertical migration, and I described that in my description of figure 7.5, happening pretty much everywhere in the whole ocean. So diel vertical migration is the largest coordinated movement of biomass on the planet, and you can conceive of it as a Mexican wave propagating around the entire planet. So tens of thousands of kilometres of scale on a twice daily basis as the sun sets and the sun rises. And there are a variety of other features listed in the panel from A to K, showing the time and space scale at which they are most prominent. And what I've tried to do in this diagram is overlay it with three common means of sampling in the open ocean. That is with ships that can go across a range of distance scales. So a typical ship survey will last for about a month and would probably cover something like, I don't know, of the order of several thousand kilometres. That's the red bounded region. The blue bounded green shaded region is the sampling time and space scale available from a mooring. So this is a device placed at one point in the ocean. So the space scale that it samples is really quite restricted. So less than probably 100 meters. But these devices can be put out into the ocean for very long periods of time, limited only really by battery capacity. So they sample in a localized area for an extended time period. And then the satellite observations is shown as white shaded and blue outline. And these can sample over very large geographic regions. So depending upon the orbit, the satellite can sample around the whole planet. And they can obviously sample for many, many years, depending again on the longevity of the orbit, the orbital stability, and the power supply in the device. So these three different modes, satellites, moorings, and ships, enable us to examine different spatial and temporal components of the global ocean. And we choose to use these devices depending upon the sorts of questions that we want to answer. So if you wanted to know, for example, what the fish stock in the North Sea was, probably a ship would be the best way to determine that, because you can't see very far beneath the surface with a satellite. And you can cover the North Sea in about a month, depending upon your transect spacing. But if you wanted to know about annual cycles of global surface production, probably a satellite would be the best way to detect that, because it's got the potential to look over the whole planet. but you might want to ground truth to satellite observations with point observations made from a ship. So the crux of this image is that it conveys the idea of time and space variability occurring together, and also gives an indication of the best sort of device to sample different sorts of variability on a global ocean scale.